So I wanted to talk today about something that my uh, PhD student Jeff Monroe and I, so I will make sure I say that, have been working on. And thanks for joining this additional lecture, whether you're here now or will be coming later. It's folks who've written papers, which is, I think, a good portion of this audience know that it can be a bit of a slog to get the rest of the details down once you have a main result, which you know how it goes. So it's nice to have a chance to share things when they're hot off the press, but then also just good to have that deadline that we gave ourselves, Jeff and I, to be done in time for this lecture. So here's a motivating, just concrete question, and we won't address the question as to why you'd want to know this, but just a very concrete question. So here's a word in the free group on 3 letters, A, B, and C. Having done a fair number of computations, I tend to like to have inverses denoted by capital letters. So this is AC, B inverse, A inverse, C inverse, A inverse, BA, B inverse, CA, B, C inverse, A inverse, A inverse, B inverse, AB. Where is it in the lower central series? So what the lower central series is the following, and this is true for any group. Well, you just start simply enough. Gamma naught of G is G, and then you set gamma I G to be the normal subgroup generated by the commutators of the previous step with G. So you at first you have anything, then you have things which you know are commutators, then you have commutators of something with a commutator, etc. And then this filtration has a lot of sort of important properties. It was first defined by Magnus, and this is the sort of a universal filtration where if I take consecutive terms, this is naturally a Lie algebra. Again, so the bracket is just WV is take the word W, follow it by V, then take the inverse of W, followed by V inverse, and you can see that it is preserved by this filtration. And so this is a way to relate sort of highly non-commutative, highly non-linear group theory to Lie theory, which is a bit more linear. You've got a ground ring or ground field, and so anyways, it's so just a very concrete question. How can you tell whether a word is a commutator, a twofold commutator, etc.? And we're going to focus on free groups. That's in fact all that we've proven things about. So what's the plan? Well, or where did this really come from? It's really the so this is the pi1 version of these Hopf invariants. So in fact, I had hoped to be done in time for them to be contiguous with the discussions of Hopf invariants, but that was a little bit more than we could pull off. So let's recall the first example. I'll be very quick. If you're watching this recorded, you can then go back to the Hopf invariants if you need. And I'm going to make these even smaller. So recall, if I've got that kind of map from a 3-sphere to a wedge of 2 spheres, I can take the pre-images of 2 points. They're going to be 1 manifolds, and then I can co-bound one and intersect with another. And so I get the linking number is of the preimages is the first Hopf invariant. So let me also make sure. So we would have the Hopf invariant actually goes to, well, I'm going to take D inverse of the preimage of, so if this is little p, and then that's big P, and this is little q, and that's big Q, I'm going to cobound P and intersect Q. And then this is entirely analogous to the following picture, and will motivate our definitions in the latter case. Namely, if I have a map from S1, and this is a big difference, the dimension is the same to a wedge of two one spheres, then I can also take the preimages of P and Q, and well, instead of, I'll still use red points and blue points, and cobound the red and intersect with the blue, and I get some numbers still, but it makes sense, assuming the red can be cobounded. So these end up, there are signs here, and if they can be cobounded, I can still form that cobounding intersection. Zero manifolds can link in S1. So, but the standard way we would say this, if you think about these points, and let me say this is say plus, minus, plus, minus or something. This really corresponds to a letter, namely, if this is, well, let's still use P and Q, this would be P, Q, P inverse, Q inverse, Q, P, Q, Q, Q inverse, sorry. So there's a word here, and then if we think entirely in terms of the word, we can play that same cobounding game. We can take the P inverse pair, cobound it, and count the number of Q's inside, and we would get a sort of Hopf or linking invariant, letter linking invariant of 1. So let's go ahead and give one more example before we get into definitions. Another thing that we saw, another good example, the next most slightly more complicated example was a map from S4 to a wedge of 3 two-spheres, and here I could do things like take the preimage of little p and call that big P, cobound it, intersect it with the preimage of Q. This ends up being, well, codimension 1 intersect codimension 2 is codimension 3, so that's a one-dimensional object in S4. It can also be cobounded, and then I could then intersect that with R, which is the, so I've got little p, little q, little r over here. And what you can do is if you have some word, let me set it up. So if I have P, Q, P inverse, Q inverse R, and then the inverse of that, which is Q, P, Q inverse, P inverse, R inverse. If I cobound the P's, that gives me these. I intersect with the Q's. So I've got a Q here and a Q inverse. Notice that those also cobound, which is good because that's what my recipe here was for. By the way, in these, if you can't cobound, then you sort of stop at that point. And we'll talk about what that means. There's really a filtration, kind of an obstruction theoretic way to think about this. In any case, so that's sort of taking care of the d inverse of d inverse p wedge q, and then I'm going to count the r's in between, and there would be 1. So in this case, the linking of letters would be 1. So that's the idea. That's all, folks. End of lecture. Just kidding. But if you get that, well, I thought that it would be pretty easy to work out the theory. You can ask Jeff. It was more complicated than I, and I'm guessing he anticipated. But that's the idea. Is to just co-bound and intersect with letters in a word rather than with submanifolds of a sphere. The word corresponds to really a 0 submanifold of S1. So let me say, before getting into this, talk about the big difference. I've said it, but let me write it down. So between Hopf or, well, letter linking, but Hopf invariants for pi 1, and those for pi n, where n is greater than 1, is that the for the latter, the vanishing of what we might call intermediate Hopf invariants is immediate for dimensional reasons, algebraically, because some homology class in the bar complex is known to be trivial. Sorry, let me do a little. Well, for pi 1, there's really a filtration. It's more or you can really think of this as an obstruction theory. It has that flavor. In order to have something defined, you have to have something else vanish before it. Okay, so what I'm going to do is make some definitions, and then I'll show you how they work on some examples. And I've got my favorite example around. Pardon me while I navigate for a little bit. Okay, so that's the example. I'll try to go. One thing I can do here is copy some of these so that I can move them around and use them for examples. So basic definition, a list, which is what we can think of as a linking invariant set for tallying, is just a collection, and it's going to be signed. All our lists are going to be signed lists. Is an unordered set, which can have repeats, a multi-set, if you will, of pairs Li, epsilon I, where Li is just some letter, so it's equal to an occurrence of some generator A or A inverse in our word W, and epsilon I equals plus or minus 1. And what we can do is really think of these, so let me go over here. I want to make this a little bit bigger. So in our example here, I take one letter and I can include it multiple times. So I'm going to think about the letter A, and maybe I include it twice here with sign plus, here with sign plus as well, here with minus and plus perhaps. So that's indicating, so that would be in this notation, I would have, it gets a little dicey or pedantic. So I would have an A with a plus, and this A refers to that one exactly, another A with a plus, etc. So notice that what you can do is, in this case, I could have also just said that really at the end of the day, and we've got a small but not that important distinction between just saying, well, I've got this twice, this once, and this actually happens 0 times, and all of these also occur with 0. So I can also just think of this as a function from the occurrences of function from the set of occurrences of an A inverse to the integers. And in fact, what we say is that two lists are simply equivalent if they give rise to that function. So this is not a double arrow, but up to simple equivalence, it would be. Okay, so that's what we mean by a list. Those are the kinds of things that we were playing with when we were looking at the first couple examples. And then an interval is how we co-bounded things. So an interval is a consecutive non-empty set of letters. That's of course all, this is all assuming a word W around. And then what you can do is we'll actually need oriented. And then that means that the endpoints have opposite total signs. So I'm assuming I've got a word that maybe I've assigned some additional signs to the letters as in the list, and then the endpoints of an oriented interval will have opposite total signs, which the way that works is if I've got, for example, A inverse with plus, that's a minus, whereas A inverse with a minus additional sign will have positive total sign. So, and then the orientation of the interval is equal to the sign of the first letter. So orientation equals the sign of the initial letter. And right, one other little definition. I'm going to just give a few definitions and then we'll go through the examples here. Well, I guess I could, why don't I just, since it is easy enough. move this over here. And so an interval is just if these had additional signs, I don't know, and generally our intervals are going to have matching letters. So these two occurrences of B inverse have different signs. And so this is an interval. And then the sign is this, the total sign of the B plus. Yeah, as Jeff said, the orientation is a total sign. Great. It's good to have Jeff here. Okay, two more definitions, but these are all very elementary. It's fun to write something that conceivably an undergrad could with some time read, work through, and calculate. Going back to lists, the count of the list of a list, which remember is Li, a collection of that is equal to the sum of, I'm going to take the sign of Li, which is just plus if it's a generator, or minus if it's an inverse, and multiply it by epsilon I. So, and then there's a standard example to think about there. So lambda of some letter, let's say A, is going to be the list of occurrences, all occurrences of A and W with all these epsilons equal to +1. And then the count of this is going to be, is really going to tell us about, well, just the number of times A occurs, and that's encoding the image of A in what? I'm looking at the abelianization of Fn, but then I need to look at the A summand there. So that abelianization is a free abelian group, isomorphic to the integers direct sum with itself n times. There's one of those summands which we can identify with A, the particular canonical direct sum decomposition. And this counting is how you determine where a word is. You're just letting the letters be abelian and counting the total amount. It would be an exponent multiplicatively, but it's a coefficient additively. And so in general, so let me just make a side remark. I'll try to say this again. These linking is really, in this case, these linking invariants are measuring sort of derived from abelianization. So that's why I think these things, there's some substance and depth to them. I really think that this is going to be the right setting to talk about a lot of things where abelianization is a part of the story. Okay, so last key definition, if phi of a list is 0, define D inverse L to be a choice of union of a union of intervals whose endpoints, so let's call it I sub j, whose endpoints it's also, so I've got one boundary point with its sign and another boundary point with its sign, and they're opposite. These endpoints exhaust L. In other words, they are the set L. So this is what we call a co-bounding in group theory. Again, let's give ourselves an example. There we go. So I've got a list and it's coming in total degree, total count 0. So then let's make this a little bit bigger for everybody. So I can have, I don't know, some, oops. I'll use, so that's what, count -2, -3, -2, -1, 0. So that's something with count 0, with this first generator occurring twice with a external plus sign. That gives us a extrinsic total sign of total value of -2, -3. Okay, and so then we have to just choose some intervals, and I will. I just have to match things with opposite signs. So I could match this A with this A. I could also match it with that one, and then this A could be matched with that A. So the intervals are really everything in between. I would have one interval equals A, C, A, all the way down to little b, C, A. Another interval is just A, C, A, B, A. And a third interval starts at that AB there, and then ends at the AB. So that's what co-bounding is. This hopefully makes sense from the pictures, and I think I've gotten all the details right. Again, Jeff can help me if I don't. Let's see. I just realized that I'm going to stick on this board, but I think, yes. So then we can have the orientations of the intervals on the lines. The orientations proceed from, I think, from positive to, we can think of it as positive to negative or something like that. So I think this one would be going left, because that's negative, that's negative. Oh, they're all going left in this case. Great. Right, so let's, one more definition. If I have a choice, a collection of intervals, and in particular, I'm just going to really think of such collections as co-boundings. This is going to be a list itself. And so this L sub B means that this is a list of occurrences of B in the word. And so a list where each time the following occurs, I add a B epsilon. So first, B with its intrinsic epsilon, sorry, its total epsilon is in LB. Next, B is in some IJ, for an IJ in the co-bounding of the first list. And then finally, what is this epsilon prime? It's just going to be the epsilon attached with B times the orientation of this ij. So for each occurrence, so for each occurrence of these, the first two, we have that in our list. And that's what, right, so let's go back here. In this example, we had that for our LA was with the red pluses. So in this case, LA is indicated by the red pluses. Let's let LB be indicated by the green, and LA was red plus minus, and LB by the green plus minus around B's. So suppose I've got, let me make it simple on myself, put a minus there, and I don't know, maybe a minus there. And what I would do is every time a B is in one of these three intervals, I would multiply it by the orientation. So here I've got a B with a minus, but I've got three occurrences. So really, and then, so what I'm going to do is now D inverse LA is chosen, wedge LB are going to be the purple plus minuses. And here, the first B is in all three intervals, so it gets three minuses. The second B is in, capital B is in two of them, so it gets two minuses. Remember, it's a B inverse, so that would ultimately count plus. And this B here is also, oh wait, and those are the only green ones. This first green plus didn't occur. So I would get a total count of that purple of -3 plus 2, which would be -1. So, so those are the group theoretic ways that we count, which is really kind of some image and abelianization, co-bound and intersect. And co-bounding and intersecting are linking. Okay, let me just give a little notation and then state the main theorems. So instead of having something like, let me just give you an example. So instead of, suppose I took something like this, I had D inverse of this canonical list, lambda C, wedge some other list. So we can iterate these. And that other list looks as follows. I'm going to take D inverse of D inverse lambda A intersect lambda B intersect lambda C, and then that's intersect lambda A. So that's a mouthful. There's a lot of D inverses. In parentheses, we're starting with these canonical lists. Again, this is just taking our Hopf invariants in higher dimensions and translating them to this setting. But this idea of every co-bounding, I'm going to put parentheses around something. And instead of my original name, every intersection, I'm going to just omit. It's just juxtaposition. And every lambda L, I'm just going to use L. And then this has a much shorter name, entirely no data lost So D inverse lambda C becomes a parentheses around C, because again, D inverse is parentheses and lambda L just becomes the letter L. And this becomes juxtaposition with, then I've got D inverse of A, B with C, and then I've got intersected with A. And even though in the all right, so even though there was sort of an order to these D inverses, these wedges, well, wedges associative, so I really didn't need that second set of parentheses, this set here. I will kind of mark out because things are associative in a sense. So, so we call those symbols for these letter linking invariants. And again, you've got these just parenthesized words. With, well, what do we have? We're going to have one more letter. Then a set of parentheses. And every set of parentheses has exactly one unparenthesized or free letter. So in this example, we see that this first parenthesis, which contains only C, that's a free letter. Here, C is also the free letter. It doesn't have to be. And for the whole thing, we would say A is the free letter. Right. And then what we're going to do for such symbols, sigma, we're going to let the function phi sigma, it's going to be defined on some subgroup of the free group. In fact, basically a lower central series subgroup, more or less, depending on how we want to set things up, is going to be phi of lambda sigma for some choice of lambda sigma for with constructed by iterated linking, so iterated co-bounding and intersection, and that's going to be according to sigma. And then the main theorems are first, that this is independent of all choices. And that's both on the phi sigma side, the co-boundings, et cetera, and also on the W side. W is a word in the free group. You could, there's not too much you can do. You can insert AA inverse pairs. Phi sigma is defined on, we talked about the lower central series, so gamma I Fn modulo gamma I plus 1 Fn. So there's a few statements here. First of all, that if where sigma is has in parentheses, so let sigma have in parentheses, we say depth in. then it's defined on that free group. So that means that you can take D inverses as you need there to just to make these co-boundings, to follow the recipe that sigma is saying. And that if I happen to be one more, if I'm in an infold commutator, if I happen to be in, sorry, I messed this up. So I said sigma is depth in. So for any I free group, no, let me keep it as it is, because this is how I normally say it. We've got the free group, I plus 1 is stated, but this is I parentheses. That's what's got to match up. So then it vanishes on any I plus 1 fold parentheses. And then the collection of these phi I or phi sigma span the homomorphisms from this subquotient, which is, and all of these together, again, form a Lie algebra, span the homomorphisms into Q. So that's the main theorem that we prove. And we also, in proving it, we need to, there's various properties, ways to compute, etc., that we have to develop in that process. But this sort of encapsulates the main goals. Let me remark, this then gives these give an alternative, therefore, to Fox derivatives, which span the homomorphisms into Z, so in that sense are better, but they seem, at least by hand, which at least by hand are much more cumbersome to calculate. So let's see, what do we want to do here? There's a few things that we could. I want to make sure my instinct is to go and look at another concrete example, so everybody sort of just sees what the definitions are, and then relate these to some other things that we've been talking about, namely Lie coalgebras, graphs and trees, and all that jazz. Let me navigate to where I have an example. And it's going to take a little bit to get there. I did this one ahead of time. So let's consider this example. Go through these ideas, because it helps to, at the very least, I want to make sure people understand the basic definitions, and then we'll see what people would like in terms of further discussion. So, so first, this says that I want to take, this is our shortened symbol, so to speak. This was shorthand for take the list of occurrences of A, co-bound it, intersect that with the list of occurrences of B, co-bound that, intersect that with the current occurrences of all occurrences of C, co-bound that, and intersect that with a list of all occurrences of B. So that's the recipe when I have this little sigma here. Notice that B occurs twice. That's perfectly fine. The main thing is that these free letters don't stack up. So I meant to say that before. If I did something like this, if I did A, B, I could even have a C here, but B or something like that, and then maybe another A. That's bad because this B is the same as the free letter here. So these free letters in consecutive sort of depths should not coincide. So so that's what this means, and let's just see how this works graphically. So I went through it, but I'll make the marks again. I just wanted to make sure I was going to do it correctly. So that's why I did it ahead of time. So the first thing I should do is take the lists of A, and those happen here. I'm going to give them uniformly positive signs for lambda A. So lambda A is going to be this set of pluses, indicated by this set of pluses. Every A occurs once with a plus, but the total signs alternate in this case from plus to minus, minus to plus, plus to minus, and minus to plus. And so then I cobound. So these are the coboundings. So these intervals are what are indicated by the inverse of lambda A. I then have to intersect those with B's, and I get a B here, which was a B inverse. So so the extrinsic sign would be a plus, but the total sign would be a minus. Here I get an extrinsic sign of minus and a total sign of minus. Here, because this interval, and that's because these intervals are oriented, left to right means an extrinsic sign of plus, right to left means an extrinsic sign of minus, and I get a total sign of minus. Right to left means an extrinsic sign of plus, and in this case I get a total sign of plus. And right to left means I've got an extrinsic sign of minus, and then because this was a B inverse, I've got a total sign of plus. I pair those off, and I've got, so what are these blues? They are the cobounding of, I took the cobounding of the list of A's, I intersected with a list of B's that had 0 count. Everybody canceled with one each other, so I can cobound again. And then finally, I intersect those with C's. There's sort of 4 spots of intersection. Let me write those a little bit more clearly. There's a plus, there's a 1 spot of intersection here, 2 minuses. And again, I intersect, or I cobound with those intervals. And then finally, I'm going to count the B's in purple that are in those intervals. And there's 1 here, corresponding to that B, 1 here, corresponding to that B. And this interval was oriented from plus to minus, so that's a plus, that gives me 0. And this is from minus to plus, so this is a negatively oriented interval. I intersect a single B with a, which occurs positively with that for a total sign of -1. Okay. And you're going to have to believe me that the corresponding calculations for a, so this is what so in fact, first let me tell you what this, this word is. Did I not transfer that to my notes? I might not have transferred that to my notes, but in fact, this word is a, is a threefold commutator. It's a commutator of pairs of commutators. So in fact, you would expect this ABC to vanish, and all other such that you can calculate will always vanish. And in this case, this further count shows that this is not in the next LCS filtration. Okay, right. So that is basically the definition. I feel like we've covered those very well. Let me move over and then say some words about the proof. I think I'll go a little bit long, but not terribly long. So some ideas of proof. First, even though we have these symbols with that are with parentheses that are that we use directly. Let me just say one more thing. So no, I'll say that in a second. So you bring in, even though it wasn't apparent in the definitions, you bring in bring back the Lie coalgebraic bar construction. So even though we have these symbols, we're going to take the Lie coalgebraic bar construction, and this would really be on the cochains of a wedge of spheres with as many one spheres as I have free group generators. So, and again, and even weight reduction. So remember this Lie coalgebraic bar construction, I have things like this. Let's do that. So I can take my D inverse of A connected to these, and that would co-bound this plus, then I have to multiply, and you start seeing these symbols. So I contract the first edge and I get D inverse of A times B. I'll use the wedge symbol, and then and these would all be, I think, plus D inverse A wedge B. This will not be a valid reduction, actually. I'll go ahead and give the third term, but this is bad because this has B as a free letter, and this, of course, also has B as a free letter. So I don't want to play that game with D inverse of A. I suppose what I need to do is what? If I do either of the B's, that will still give me a bad edge. If I do the C's, right, so I have to do the C first. So this is hit by the following thing as well, D inverse C, B, B. And then I've got one edge to contract, and I get D inverse C, wedge A, B, B. Now I'm going to pick on one of these B's. This is the same weight reduction we did before. So I'm going to take D inverse C, wedge A, to D inverse B, to B. And then if I, the other term I get in contracting edges, contracting that edge is, yeah, because any other time I take a D, I'm going to get 0. So I really have to think about just contracting the one edge. And then that's going to be what? D inverse C, wedge A, wedge D inverse B. And then that's still connected to a B, and I can do that any way I want. Ultimately, let me catch up with writing over here. Ultimately, I'm going to get something like D inverse C, wedge A, wedge D inverse B. I'll take D inverse of that, wedge B. And this, again, corresponds to a much simpler symbol there. So my original graph, one way I could reduce it, and my graph had what? An A, two B's, and a C. So weight reduction in this setting takes a graph to a symbol. And basically what we show is that the linking of letters, so what's again conceptually going on. So, what we're doing is we, philosophically, we think of functionals on the free Lie algebra as easy. And that's something that Ben Walter and I do operatically. So the free Lie algebra is, free Lie algebra is a direct sum of Lie I on some vector space V, tensor V, tensor I, over the isometric group. And so the dual co-free Lie coalgebra is something that we make from graphs. The star here means linear dual. So we think of that as easy. And so you're trying to lift these easy functionals. It's not really lifting, but it is once you're in a commutator subgroup, then you're lifting from that quotient by the next commutator subgroup. But first you have to know that you're in a commutator subgroup. So we're trying to lift these easy functionals to the free groups, lift or really extend to the free groups themselves. And what we do is we show the key theorem. And again, this is with Jeff and myself, is that if some graph G reduces to a sum of symbols, but I'll just think of that as a single symbol sigma, then this is, I'm not going to make a super precise statement as I've set it up, but then this phi sigma on some word is going to equal to the sort of the graph value on Lie element associated to the word. So this is what I haven't defined, but e.g., well, if W is like A, B, C, then you've got the same Lie element. Otherwise, you have to make that translation, but that's standard. So we show that these linking invariants are exactly given by previous things that Ben Walter and I defined Lie, very graphical ways to deal with Lie algebras and coalgebras. So then let me say what's next, and then we'll finish up. Well, from free groups to other groups. So for example, if G is pi1 of a genus 2 surface, which remember is generated by, say, A, B, C, D, such that the commutator of AB times the commutator of CD is the identity, then you would, so then you don't have, well, then AC is still defined, at least if you're in the first commutator subgroup, but and it's still well defined. So what is that again? That's counting C's which occur A and B, and that's because there's no relation with commutators of A and C, but A, B is not, and I should just say well defined here, but A, B minus C, D is. Yeah, so there's just gonna, you need to, so you can start with the Lie coalgebraic bar construction on the cochains of X, where pi1 of X is G. You can just think of X as a two-cell complex. But the one difficulty that I see so far is that we need, for these linking invariants, again, we have things like the linking of A and B, and then with B again was not allowed. And so translating that condition to the Lie coalgebraic bar construction is something I don't see how to do. But I mean, once I bring the cochains in, you could also imagine you can see what the consequences of this would be for non-simply connected rational homotopy. And the idea is, and you would expect in general, at least if you're going to take the Quillen model and the Sullivan model, that you would really see the fundamental group using cochains through these linking invariants. So in a sense, we're offering a question: how can cochains see pi1? Well, first of all, we're giving up a bit, and we're only saying we're going to understand the lower central series Lie algebra, which is all you'd expect in the Quillen-Sullivan setting. That's all we're going to see, and we're going to see it through these linking invariants. So that's the idea. Now, people like Manuel Rivera have been doing some fun things with bar constructions and fundamental groups. And there's a group there's BUIJS. My apologies for not knowing how to pronounce that name. Weech, Murillo, I guess Felix and Tanray have some non-simply connected rational homotopy based on the Lawrence Sullivan, the Lawrence Sullivan cone object. And so this is kind of seems like we're coming back to non-simply connected rational homotopy from a couple of ways. And this is something now that we've got the free group setting done that we can play with this. All right, let me stop there. I'll open it up to questions. I can even unmute people or just do it in the chat. And if there's no questions right away, what I'll do is I'll stop the stream and then see if people were just shy with the live